Discovery of fundamental particles. The discovery of atomic particles began with the electron, and that journey started with cathode ray experiments. Hatchuk H2, Discovery of Electron Experiment by J.J. Thomson, 1897. He discovered electrons using a special glass tube experiment. H3, what are cathode rays? Cathode rays are streams of electrons. They start from the cathode, negative electrode, and move toward the anode, positive electrode. H3, evidence, fluorescence, and shadow. When cathode rays strike certain materials, like zinc sulfide, they cause them to glow. This glow is called fluorescence. When an object is placed in the path of rays, it casts a shadow, proving they travel in a straight line. H3, particle nature of cathode rays. Cathode rays are not light waves. They're actual particles, electrons. They can rotate a mica wheel placed in their path, showing they have mass and kinetic energy. This proves their particle nature. H3, charge on cathode rays. Cathode rays are negatively charged. They get deflected by electric and magnetic fields, just like any charged particle would. H3, X-ray production. When cathode rays strike metals of high atomic mass, like tungsten, they produce X-rays. H3, properties of cathode rays. 1, travel in straight lines. 2, have mass and kinetic energy. 3, rotate light objects like mica wheel. 4, have negative charge. 5, can ionize gases. 6, produce fluorescence on hitting materials. 7, can generate X-rays when hitting heavy metals. 8, emerge from cathode. 9, specific charge is constant, no matter which gas is used. Would you like to quiz yourself on the emojis for easy understanding? H1, Millikan oil drop experiment. Charge electron ki daryaft. H2, purpose of the experiment, to determine the exact charge on a single electron. H3, the setup. A fine mist of oil droplets is sprayed into a chamber. X-rays are passed through air, which ionizes gases like oxygen and nitrogen, releasing free electrons. These electrons attach to oil droplets, making them negatively charged. H3, applying electric field. A variable voltage is applied between two plates. The electric field acts against gravity. At a certain voltage, the oil drop becomes stationary, meaning electric force, gravitational force. H3, charge calculation by balancing the forces and using known values, mass, voltage, gravity. Millikan calculated the total charge on a drop. H3, key conclusion. Charge on oil drop is always a multiple of a basic unit, Q equals N dot E, where QT equals total charge on drop, N equals integer 1, 2, 3, E equals elementary charge equals 1.6 times 10 to the sine Cs. This proves that charge is quantized. H3, why it matters. First accurate measurement of electron's charge helped determine the mass of an electron using the E/m ratio from Thomson's experiment. H1, discovery of proton and anode properties. Proton ki daryaft or anode khususiyat. H2, anode, the positive side. The anode is the positive electrode in a cathode ray tube. It plays a crucial role in identifying positive charges. H3 anode, particle nature, like cathode rays, anode rays, positive ions, also travel in straight lines. These rays cast a shadow when blocked by an object, showing they travel in a straight path. H3, anode rays have kinetic energy. Anode rays have kinetic energy, and their particle nature is evident because they can rotate a mica wheel placed in their path, just like cathode rays. H3, charge of anode rays. Anode rays are positively charged, unlike cathode rays, which are negatively charged. They get deflected by electric and magnetic fields, but in the opposite direction compared to cathode rays. Changing gases affects specific charge. The specific charge per unit mass of anode rays can change depending on the gas used in the tube. Color of the rays also changes based on the gas used. For example, hydrogen produces a pinkish glow, while neon gives an orange glow. H3, charge to mass ratio. The specific charge of anode rays is not constant across different gases. It changes as the gas type changes. H3, anode rays do not emit from anode. Anode rays do not emit from the anode itself. They originate from ionized gas particles in the tube. H3, discovery of proton, the study of anode rays, led to the discovery of the proton, the positively charged, which is the main component of anode ray. Thomson's atomic model, Pitting model, also known as the plum pudding model, Thomson-Ka-Itmi model. H2, the model's basics, proposed by J.J. Thomson in 1897 after the discovery of the electron. The atom is composed of a positive charge spread throughout the atom with electrons embedded within it, like raisins in a pudding. H3, structure of the atom in the plum pudding model. Positive part of the atom is the pudding, the solid, positive charge. Electrons, the raisins, are scattered inside the positive charge. Overall, the atom is electrically neutral because the positive charge balances the negative charge of the electrons. H3, problems with the model. This model couldn't explain the stability of the atom. It also couldn't account for how electrons could stay inside the atom without spiraling into the nucleus. H3. H3. Limitations. The plum pudding model was later disproved by Rutherford's gold foil experiment, which showed that the positive charge is concentrated in a small nucleus at the center of the atom. Rutherford's atomic model, Rutherford-Ka-Itmi model. H2, the Rutherford gold foil experiment, alpha particles, these are positively charged helium nuclei. A thin gold foil was bombarded with these particles. A zinc sulfide screen was placed around to observe the scintillations, flashes of light, when alpha particles struck. H3, key observations. 1. Most alpha particles passed straight through without deflection. 2. Some were deflected at small angles. 3. A very few were deflected more than 90 degrees, meaning they bounced back. 4. Deflections were observed as tiny flashes on the screen. H3, mathematical observation. The number of alpha particles deflected, Schraffel 1, Sanwin-Berger sin, Theher 2, Taffer The equals angle of deviation. Also, inversely proportional to the kinetic energy of alpha particles. H2, conclusions of Rutherford 1. Atom is mostly empty space, since most particles pass through. 2. Mass and positive charge of the atom are concentrated in a tiny, dense nucleus. 3. Electrons revolve around this nucleus in orbits, like planets around the sun. Number 4. Atom has a spherical shape overall. H2. Limitations of the Rutherford model. 1. Could not explain atomic stability. According to classical physics, revolving electrons, charged particles, should emit energy. This would cause electrons to spiral into the nucleus, but that doesn't happen. 2. Failed to explain line spectrum of atoms. Rutherford's model predicted a continuous spectrum, but in reality, atoms emit discrete line spectra. H3, importance of Rutherford model. It introduced the nuclear concept of the atom, laid the foundation for Bohr's atomic model, which resolved these limitations. Herr Rutherford and Bohr's atomic models, and Rutherford atomic model, based on classical laws of physics, quantum theory of radiation. Postulates. 1. Atom consists of a dense nucleus at the center. 2. Electrons revolve around the nucleus in circular orbits like planets around the sun. 3. Most of the space inside the atom is empty. 4. Electrons lose energy due to radiation, so according to classical theory, they should spiral into the nucleus, but this doesn't happen. Limitations. Couldn't explain the stability of atoms. Couldn't explain line spectra. Valid only for hydrogen and hydrogen-like atoms. H2 Bohr atomic model. Applicable for only hydrogen H and hydrogen-like atoms, each Li 5, etc. Main postulates. 1. Electrons revolve in fixed circular orbits shells. 2. Only those orbits are allowed where angular momentum, MVR equals NH2 pi, has. Important notes. Electrons do not emit radiation while in stationary orbits. Energy is emitted or absorbed only when an electron jumps between orbits. This explains the line spectrum of hydrogen. H2, important formula in mnemonics. Radius of nth shell, hydrogen-like atoms, R cake n quarized by Z, mnemonic, ran 2s. R equals radius, n quid equals n quadrated, Tz equals Z. Velocity of electron in nth shell, V to Z n. W equals velocity, Za equals Z, n equal n. Energy of electron in nth orbit, E minus Z quart of n square n mnemonic. Izat do, izat equals E, do equals Z Friday by na do equals slash n Friday. Potential energy minus 2 minus kinetic energy. Total energy equals mass kinetic energy. Can excited state, electron in X excited state lies in shell equals X plus 1, e.g. second excited state, shell equals 2 plus 1, third shell. Separation energy, energy required to remove electron from excited state to infinity, ionization. Hash-Fraeniger, H2, limitations of Bohr's model. 1. Could not explain atoms with multiple electrons. 2. Could not explain splitting of spectral lines in magnetic field, Zeeman effect, electric field, Stark effect. 3. Could not explain dual nature of matter. 4. Fails for high-speed electrons or relativistic corrections. Sommerfeld's extension of Bohr's model, Bohr-Marikitosia Bedria, Sommerfeld. H2. What is Sommerfeld's extension? Bohr's model said that electrons revolve only in circular orbits, but Sommerfeld said not all orbits are circular, some are elliptical too. H2, key postulates. 1. Each principal shell, n, is made up of subshells, also called energy levels or orbits. 2. The number of subshells equals principal quantum number, n, for n equals 1, 1 subshell, for n equals 2, 2 subshells, and so on. 3. The first subshell is circular, the rest are elliptical. 4. Electrons in same subshell have the same energy in hydrogen and hydrogen-like atoms. H2. Types of subshells based on quantum numbers. Shell n, subshells L, shape, mixed, 1, 1, 0, S, circular S, 2, 0, 1, SP, S equals circular, P equal elliptical, 3, 0, 1, 2, SPD, mixed, 4, 0, 1, 2, 3, SPDF, mixed. H2. What did it solve? Explained fine structure, splitting of spectral lines. Brought the idea of energy level substructure. Laid the foundation for azimuthal quantum number L in quantum mechanics. Let me know of light and radiation. Roshan ki dohari fitrat. H2. Wave nature of light. Maxwell's electromagnetic theory. 1. Light is an electromagnetic wave. 2. It has electric field oscillating in one direction, magnetic field oscillating perpendicular to it. Both fields are perpendicular to the direction of propagation. 3. Speed of light c equals a nu lambda, speed equals frequency, wavelength. 4. All EM waves, like radio, micro, visible, UV, X-ray, gamma, travel at 3, 10, 10 to meters per second in vacuum. 5. Do not need any medium to propagate. H2, phenomena explained by wave nature, reflection, refraction, diffraction, limitation of wave theory, cannot explain blackbody radiation, photoelectric effect, electric effect, line spectra of hydrogen atom, particle nature of light. Based on quantum concept, light also behaves like particles, called photons. Each photon carries a discrete quantum of energy, E equals h nu, where E equals energy. EH, Planck's constant, 6.626 times 10 quarter J's, E frequency of light. And Spencer entered H2 phenomena explained by particle nature, photoelectric effect, blackbody radiation, hydrogen line spectrum, and H2 dual nature concept. Light behaves both as nature explains, wave reflection, refraction, interference, diffraction. Particle, photoelectric effect, black body radiation, line spectra. Let me know when you're ready to Planck's quantum theory and photon concept. Planck nazariya quantum or photon ki khususiyat. H2, key postulates of Planck's quantum theory. 1. Energy is not emitted continuously, but in small discrete packets called quanta. 2. For light, the quantum is called a photon. 3. Energy of one photon is directly proportional to its frequency. E equals h nu, where E energy of photon, h Haki equals Planck's constant equals 6.626 times 10 minus 34 tech J's. Ni equals frequency of radiation. 4. If n photons are emitted, E text total equal nh. Hapard H2 properties of photon, property. Description like particle, neutral, no charge, rest mass, 0, 0. Speed of light 3 times 10 to 8 men per sec. Travels like wave, absorbs like particle. Requires medium, no medium needed for photon to travel. Hacha H2. Momentum of a photon. Since photon has energy and behaves like a particle, it also has momentum. Formula 1, P equals frac H lambda. Formula 2, using energy, P equal frac EC, where minus P equals momentum, equals wavelength, E equals energy, C equals speed of light, TH equals speed, and force. Force 5 twice 1 tons. Radiation, pressure, and force. F is the power of radiation. Pressure of photons, frac intensity, C. H2, important note, energy and frequency are additive in nature. Wavelength is not additive in nature. If energy travels, it behaves like it has mass, thus momentum. Includes equations, photoelectric effect, photoelectric effect. H2, key characteristics of photoelectric emission. 1. Number of photoelectrons emitted per second. Rate of emission is directly proportional to the intensity of incident light. Text intensity. 2. Energy of incident photon is used in 2 parts. To overcome the work function, phi, remaining part becomes the kinetic energy of emitted electron, E equals phi plus Ke, where E equals hν, energy of photon, fraternity phi, we equal work function, minimum energy to eject an electron. Ke equals kinetic energy of the emitted electron. H2, work function phi, minimum energy required to eject an electron from the metal surface, depends on material of the metal. If H nu phi, no emission occurs. H2, frequency and wavelength relations. Threshold frequency, neen zero, minimum frequency required to eject electron. Text only if nu g nu 0, right arrow text emission occurs. Threshold critical wavelength, Legman-Serbs for maximum wavelength that can cause emission lambda 0, frax C nu 0. H2, effect of changing frequency and intensity, parameter on emission, effect on emission, ni. Frequency, ni kinetic energy, but photoelectron count same. Intensity, number of photoelectrons, but Ke same. H2 stopping potential, V0. The minimum negative potential applied to the collector plate to stop the photoelectrons with maximum kinetic energy. EV equals Ke text max equal nu minus phi, where minus E charge of electron, V self-kinetic state equals stopping potential. Ke max equals maximum kinetic energy of electrons. Getting good, important graphs. 1, Ke versus frequency, ni straight line with slope h. My x-intercept equals threshold frequency energy. 2, photoelectric current versus intensity, linear graph. Intensity, current. 3, photoelectric current versus voltage for fixed sten. Saturation current observed. Reverse voltage equals stopping potential. Would you like Ke versus frequency, ni straight line with slope h. My x-intercept equals threshold frequency energy. 2, photoelectric current versus intensity, linear graph. Intensity, current. 3, photoelectric current versus voltage for fixed sten. Saturation current observed. Reverse voltage equals stopping potential. Spectrum, wavelength, frequency, and hydrogen emission series. 1, arrangement of radiations based on increasing wavelength, gamma, X-ray, UV, visible, infrared, microwave, radio. Based on increasing frequency, neen, radio, microwave, infrared, visible, UV, X-ray. 2, emission versus absorption spectrum. Emission spectrum, absorption spectrum, and infrared formed when atoms emit energy as light. Formed when atoms absorb certain wavelengths. Observed when heated or energized gases emit. Observed when white light passes through a gas. Shows bright lines on dark background. Shows dark lines on continuous spectrum. 3, types of spectrum. Continuous spectrum. All wavelengths present, no dark spaces from hot solids or dense gases. Discontinuous spectrum, only specific wavelengths, dark spaces in between from excited atoms like hydrogen. Emission spectrum of hydrogen and hydrogen-like atoms. Electrons in lower energy orbit equals minimum energy. To jump up, electrons absorb energy. To fall down, electrons emit energy. This emitted energy gives line spectrum. 5. Hydrogen spectrum series N un fixed, N2 varies. Series N nun, region nin, Lyman. To jump up, electrons absorb energy. To fall down, electrons emit energy. This emitted energy gives line spectrum. 5. Hydrogen spectrum series N un fixed, N2 varies. Series N nun, region nin, Lyman 1 ultraviolet, Balmer 2 visible, 3 infrared, bracket 4 infrared, Fun 5 infrared, Humph 6 infrared. Mnemonic L. Az Boys prefer being perfectly happy. Nadshaw 6. Redberg formula equals RZ2 frac 1 and 1 frac 1 and 2 2 2 right. Where lambda equals wavelength of emitted photon, R equals Rydberg constant equals Stern 1.097 times 10 cent, Z equals atomic number, Z equals 1 for H, N1 equals lower orbit, N2 equals higher orbit, N2, N1 for hydrogen. For frac 1 equals 912 angstrom approx. Dampschon 7. Number of spectral lines. To calculate number of lines when an electron jumps from orbit N2 to Ne, number of lines equals frac N2 minus N1, 2 times 2N2 minus 2N1 plus 1. For ground state, N1 equal N1 number of lines equals for frac N minus 1, 2 electron. Hard 1, de Broglie hypothesis, proposed that particle wavelength and wave nature of electron. Hard 1, de Broglie hypothesis, proposed that particles like electrons also have wave nature. The wavelength associated with a moving particle is called the de Broglie wavelength. Lambda equal frac hmv, where lambda equals wavelength, h equals Planck's constant, 6.626 times 10 minus beef JS, m equals mass of the particle, v equals velocity of the particle. Number star 2, standing wave condition in shells, Bohr's orbits. According to Bohr and de Broglie, text circumference of orbit equals amda. 2 pi r equals amda. This means only those orbits are allowed where electron's wavelength fits exactly into the circular orbit. N equals shell number, also the number of wavelengths that fit into the orbit. 3. Angular momentum from de Broglie concept. Using lambda equals frac h mv and quad 2 pi r v equals n lambda. Substituting lambda, 2 pi r equals n left mv right. Right arrow mvr equals frac nh 2 pi. So boxed. This matches Bohr's quantization condition for angular momentum, showing de Broglie's idea supports Bohr's model. Key points to remember. Electron behaves like a wave while revolving in an atom. De Broglie's wavelength explains why only certain orbits are allowed. Each orbit has integral number of wavelengths. Supports the quantization of angular momentum. Heisenberg's uncertainty principle. Basic statement. It is impossible to determine simultaneously the exact position and exact momentum of a subatomic particle, like an electron. This principle reflects the wave-particle duality of matter and the limits of measurement at quantum levels. Mathematical expression, delta x, delta p, gq frat 4 pi, where delta x equals uncertainty in position, delta p equals uncertainty in momentum, momentum equals mass velocity. H equals Planck's constant, 6.626 times 10t, just interpretation. If you try to precisely measure the position, the uncertainty in momentum increases. If you try to precisely measure the momentum, the uncertainty in position increases. This is not due to instrumental error, but a fundamental property of nature. Angular version for angular momentum, angular position, delta theta, delta h frac 4 pi, where delta theta equals uncertainty in angular displacement. It's uncertainty in angular momentum. On why it matters. This principle sets a limit to what can be known and calculated in quantum mechanics, and it also explains why electrons cannot be found orbiting the nucleus in fixed paths like planets. Instead, they exist in probability clouds, orbitals. Quantum mechanics and wave nature of electron. Wave nature, proven by experiments. Davison and Germer experiment. Electron beams scattered from a nickel crystal, forming concentric rings on a photographic plate, just like X-rays. This proves that electrons have wave nature, similar to light. Thomson's experiment also confirmed wave nature by showing diffraction patterns of electrons. Atomic structure, shell, subshell, and orbital. Shells, represented by principal quantum number n, subshells, represented by azimuthal quantum number L, orbitals, 3D regions around the nucleus where the probability of finding an electron is maximum. Classical versus quantum mechanics. Macroscopic particles follow classical mechanics, e.g. Newton's laws. Microscopic particles, electrons, protons, follow quantum mechanics because of a wave-particle duality. Schrödinger wave equation provides the wave function psi of a particle. The square of the wave function, psi square 2, gives the probability density of finding an electron. Acceptable wave function conditions. For a wave function psi to be physically meaningful, 1, it must be finite. 2, it must be continuous and single-valued. 3, the total probability over all space must be equal to 1. Horror. Eigenfunctions and eigenvalues. Only certain solutions of Schrödinger's equation are significant. These are called eigenfunctions, and their corresponding allowed energies are called eigenvalues. These eigenfunctions describe allowed orbitals where electrons can be found. Would you like a chart of quantum numbers, the address of an electron? Quantum numbers are like the complete address of an electron inside an atom. Just like your home address has a flat number, street, area, and zip code, an electron's location is described using 4 quantum numbers. An electron's location is described using 4 quantum numbers. One principal quantum number n, the city, n, values 1, 2, 3, 4. KLMN shells tells us about main energy level or shell, size of the orbital, distance from the nucleus. Higher n equals higher energy. Formulas: orbitals equals n squared, max electrons equals 2n squared. 2. Azimuthal quantum number L, the street subshell. Symbol L values 0 to n minus 1, L equals 0, L equals 1, P, L equals 2, D, L equals 3, tells us about shape of the orbital, type of subshell. Angular momentum, L equals LL plus 1, diffrac H 2 pi. Orbitals in subshell, 2L plus 1. Electrons in subshell, 2 times 2L plus 1. 3. Magnetic quantum number, or M or ML. Building direction. Symbol VEMA used from minus L plus L including 0 tells us about orientation of orbital in space, important in magnetic field situations, Zeeman effect. Example, L equals 1, P orbital, M equals 1 and 0 plus 1, 3 orbitals, 3 orbitals, P she, P that, P and 4. Spin quantum number, flat number. Symbol, MS, values 2, or magnifrac 1, 2. Tells us about the spin of the electron, like clockwise or counterclockwise, purely quantum behavior, no classical analogy. Every orbital has 2 electrons with opposite spins. Summary table, electron's home address, quantum number, symbol, what it describes, analogy, emoji, orbital orientation, princip n, main energy level shell, city. Azimuthal, subshell and orbital shape, hadrit. ML, orbital orientation, building direction. Want a visual diagram, graphical representation. Nodes are points or regions where the probability of finding an electron is 0. TAS equals 0 or R equals 0. 1. Types of nodes. There are 2 main types of nodes. A, radial, spherical way. Nodes found in spherical shells. Probability is 0 at a specific radius from the nucleus. Formula text. Radial nodes equals n minus L minus 1. B, angular nodes, found in non-spherical shapes, P, D, F orbitals. Probability is 0 at specific angles or planes. Formula, angular nodes equals L. 2, total number of nodes. Total nodes, n minus 1. Ha3, node summary table. Orbital, n, L. Radial nodes, angular nodes, total nodes equals 0 probabilities. 1s, 1, 0, 0, 0, 0. 2s, 2, 0, 1, 0, 1, 2p, 3p, 3, 1, 1, 1, 2. Strufor, node equals 0 probability. A node is a point where probability density equals 0. For example, electrons can never be found at a node. 5. Graphical representation. S orbital spherical wave function cosine type wave, radial distribution function, always sinusoidal. Phases, number of phases, n minus L. Each phase represents a region between nodes. Graph features, last phase never touches R axis, RDF is never negative. Peak height increases with each phase. P orbital, wave function, sine type wave, electron distribution along a straight line dumbbell shape, one angular node, a plane through the nucleus. Summary of phase and RDF. Property, description, Mingekin. Wave function for S, cosine wave function for P, sine number of phases, N minus L, RDF behavior, always positive and sinusoidal. RDF peak increases with successive phases. RDF end behavior. Last phase doesn't touch R axis. Would you like orbitals? Orbitals are 3D regions in an atom where the probability of finding an electron is high. Their shapes arise from combining. Radial wave function R depends on distance r from nucleus. Angular wave function Y depends on direction phi. 1. S orbital. Shape, spherical and symmetrical. Wave function, radial only, no angular node. Electron density, uniform in all directions. Node planes 0, L equals 0 for 2. Shape, dumbbell shaped along axes. Types, px along x-axis, pi along y-axis, pz along z-axis. L equals 1, one node plane. Angular node, a planar region where probability equals 0, electron density concentrated on both sides of nucleus. Schrödinger 3, d orbitals. Total 5 d orbitals when L equals 2, number of node planes equal 2. Types of d orbitals and their electron density orientation. Orbital, symbol, electron density orientation. D sine sub xy, tb, 2 between axes, xy plane, d of yz, tween yz, xz, t sub between axes, xz plane, d sub x squared minus y squared, e.g., along x and y axes, high on axes, e.g., along z-axis plus donut, z-axis torus. Here 4, node plane. A node plane is a flat region where electron probability equals 0, number of node planes, azimuth of the quantum number L. Quick recap table. Orbital value of L, shape, node planes, orientation feature. S0, 0, spherical, 0, symmetrical in all directions. P1 dom 1, along x, y, z axes, D2, clover donut, 2, between along axes. The Aufbau principle explains how electrons are filled in orbitals of atoms in order of increasing energy. Key rules. 1. Electrons are filled in orbitals in the order of increasing plus L value. N equals principal quantum number, energy level. L equals azimuthal quantum number, subshell type. S equals 0, P equals 1, D equals 2, F equals 3. N plus L's determines the energy of an orbital. 2. If two orbitals have the same n plus L value, the one with lower n is filled first. Lower energy equals filled first. Schneider-Scarf example. Orbital n, L, n plus L, order of filling, 1s, 1, 0, 1, first 2s, 2, 0, 2, second 2p2, 1, 3, third, 3s, 3, 0, 3 highs. Fourth, 3p, 3, 1, 4, fifth, 4s, 4, 0, 4, sixth, 3d, 3, 2, 5, seventh, 4p, 4, 1, 5, eighth. Use filling pattern using arrow diagram. Remember this chain for filling orbitals. 1s, 2s, 2p, 3s, 3p, 3d, 4p, 4d, 5p, 6s, 4f, 5d, 6p, 7s, f5, f6d, 7p. Use diagonal rule Aufbau arrow method to follow this pattern easily. Each orbital s, p, d, f can hold orbital max electrons shape S2 sphere, P6 dumbbell, D10 clover, F14 complex. Each individual orbital, like px or devise, can hold 2 electrons only. Special case, hydrogen and hydrogen-like atoms, one electron system. For hydrogen, orbitals with the same principal quantum number n are degenerate, same energy. So 3s equals 3p equals 3d in terms of energy for hydrogen. Pauli's exclusion principle. No 2 electrons in the same orbital can have all 4 quantum numbers identical. This means Each orbital can hold a maximum of 2 electrons, and those two must have opposite spins. Example, in one's orbital, if one electron has spin nas not plus nihai phis, the other must have spin non as nihai. Important notes. Pauli exclusion principle does not explain the hydrogen spectrum that's due to other quantum effects. Hund's rule of maximum multiplicity. Electrons occupy degenerate orbitals singly first with parallel spins. Degenerate orbitals equals orbitals with same energy, like px, py, pz. Explanation. Pairing does not start until every orbital in a subshell has 1 electron each with the same spin. This ensures maximum unpaired electrons, leading to greater stability. Example, in 2p, px, pi, pz, electrons will go like this, chat, and only then chak. Why half-filled and fully filled orbitals are more stable? Symmetry. Electrons are more symmetrically distributed. Exchange energy. More possibilities for electron exchange, which lowers energy, hence extra stability for configurations like D half-filled, e.g. chromium CrAr3D4SN, D fully filled, e.g. copper Cu3DD4S. That's for exceptional configurations. Car 3D free field 4S1, not 3D with 4S Alberti, copper 3D Dzai 4SN, not 3D 4S4S. Reason, half-filled and full-filled d orbitals are more stable than expected. Degenerate orbitals equals orbitals with same energy. In absence of magnetic or electric fields, all orbitals within a subshell, like px, PAPZ, are degenerate. Magnetic moment. Magnetic moment arises due to the presence of unpaired electrons in an atom or ion. Formula, μ equals Qi n plus 2, where μ equals magnetic moment, n equals number of unpaired electrons. Unit Bohr magneton, bm. Far, quick facts. Paramagnetic substances have unpaired electrons, are weakly attracted to a magnetic field. Example, O2, Phis, μ0. Diamagnetic substances have no unpaired electrons, are weakly repelled by a magnetic field. Example, Zn quart he, m equals 0. Note for n equals 0, magnetic moment is approx 0.75 greater than the number of unpaired electrons. Blackbody radiation. A blackbody is an ideal object that absorbs and emits all wavelengths of radiation perfectly. It does not reflect or transmit any radiation. Radiation emitted depends on temperature and is based on particle nature of light, as explained by Planck's quantum theory. Important concepts introduce the idea that energy is quantized. Light shows both wave and particle nature. Helped explain failures of classical physics to describe radiation from hot bodies. And with that, this chapter is complete.